Syk model and traversable wormholes. This is a work in collaboration with Elena Caceres and Rafael Pimentel that came out to the archive some weeks ago. So the SYK model, it's been around for several years already. It's a quantum mechanical model that serves as a holographic dual as a holographic model in lower dimensions. So it's a quantum mechanical system of any Majorana fermions, and they are coupled via random interactions, J. These interactions are sampled from Gaussian with zero mean and variance that's given by this expression here that has a parameter J that sets the energy scale of the theory. And the Majoranas, they interact Q of them each time. And we take all possible combinations of Q Majorana. So this is what I am calling all to all. And the properties of this model is that it's solvable in the large N, and it has the desired properties of a holographic system, such as the emergent conformal symmetry and the saturation of the chaos bound of Maldacena, Schenker, and Stanford. And more recently, a variation of the SYK model appeared in the literature by Shu, Suska, and Su, and Swingle, dubbed Sparse SYK. It's a modification that makes the simulation of the SYK model more doable. So it allows us to explore what happens beyond this large N limit. So we can study how gravity merges as we increase N. And in particular, what we are interested in here is to see whether or not this sparse SYK model can be used to describe traversable wormhole. For the all-to-all SYK, it has been shown by Maldacena and Qi that if you take two copies of the SYK model, which I call left and right, and you add a bilinear interaction between them, like this, with some coupling strength mu, then it can be shown that in the limit of large N and small coupling, this system is equivalent to ADS2 solution that has the geometry of a traversable wormhole like this on this picture on the left. And this global ADS2 solution, it can be obtained from Jekyll tractable in gravity by adding a coupling between the two boundaries, following a mechanism similar to the one of Gao, Jaffers, and Wall from 2016. The only difference is that the interaction here is time independent, so we construct a wormhole that's traversable for any time. So what we want to do in this work is to see if we can study finite N corrections to this system, this eternal traversable wormhole, by making use of the sparse SYK model. That's our goal. So let me define the sparse SYK model. The idea is actually very simple. You just take the original model with the random interactions and the all-to-all terms, and you start deleting them. So you can introduce some coefficient x, and you can choose it to be either 0 or 1. And each choice of these coefficients is going to lead to a different sparse SYK model. And what has been shown so far in the literature is that you can keep just a few terms, order n, in this sum, in such a way that you still recover properties of the original SYK model, such as the chaotic behavior. So the question now is how to precisely choose these coefficients x to define the sparse model. There are several ways to do it. I just going to choose one that follows regular hypergraph construction. So first of all, hypergraphs are just a natural language to describe the way that the interactions in the Hamiltonian or any many-body quantum system. Since here we have more than two Majoranas interacting at each time, we cannot use just graphs. We need to use these hypergraphs, which are a generalization where you can have edges that contain more than two vertices. And the way we identify a hypergraph with the Hamiltonian is to identify each Majorana fermion with a vertex and each term in this sum as some hyperedge. And the way we are going to implement this parsing in this model is to choose a K times Q regular hypergraph, which means that each Majorana fermion is going to be contained in exactly K times Q terms in this sum. Or in the hypergraph language, every vertex is contained in K times Q hyperedges. And just to clarify the notation, Q is going to indicate the Q-body interaction in the Hamiltonian, and we introduced this parameter K that just quantifies the degree of sparsity in the Hamiltonian. If you make K smaller, then the system is more sparse. And this choice, you can just count, it makes the Hamiltonian to contain exactly Kn terms. So this is a statement about quantum chaos, needing only order n terms. Here it means that we can just have K of order 1 to be enough to reproduce the features of the ultra SYK. And to gain some intuition about the sparse model, this hypergraph language is also useful because there are several known measures that quantifies the connectivity in this hypergraph. And what we want is we want to make the hypergraph more sparse, but in such a way that the connectivity is still high, high as compared to the ultra SYK model. And one way to do this is to look at the adjacency matrix, which counts the number of hyperedges that contains two given vertices. And we can compute the spectral gap of this matrix given by the difference between the largest and the second largest eigenvalue. And we can, for example, plot for the hypergraph for the sparse SYK model, which are these solid lines. And we can see that even for K of order 1, just a little bit larger than 1, it does not change that much, its connectivity, and gets close to the dashed line, which is the corresponding value for the original ultra SYK model. So this is consistent with the previous result of quantum chaos, needing only K of order 1 to be an effective model for the ultra SYK. There are other measures of connectivity for hypergraph, like the algebraic entropy and vertex expansion, but they give more or less the same qualitative behavior.
Can you comment about out of time order correlators in this model? Are they in the same class with saturation and everything as in SYK?
Yes, so the calculation of out of time order correlators was not done. But I think what was done is the chaotic behavior, meaning that it should have the same Lyapunov exponent, but extracted in a different way. So it should also be close to maximally chaotic here.
Thanks.
Okay, so here, since I'm going to focus on this traversable wormhole, let me just review first what is known for the two-coupled SYK model for the ultra system in the large n limit. So just to remind you, we take two copies of the SYK, left and right. We add this interaction between them with some coupling mu. So this model is known to have a ground state that's close to a term field double for some temperature that depends on the coupling. And what I think it's going to be more important for this discussion is that it has an energy gap above this ground stage. And from the Largian analysis, in which the gravitational picture of a traversable wormhole holds, this gap at weak coupling, it obeys some non-trivial scaling given by this particular power here. At strong coupling, it goes like linearly in the coupling, essentially because this term dominates and the system is roughly a free fermionic harmonic oscillator. So this energy gap is important because it's going to build the connection with the gravitational limit, and it gives, for example, the characteristic frequency of oscillation of the Green's functions. So we have computed the Green's functions numerically for this sparse model. We went up to 40 Majoranas in total. And due to the presence of the interaction, if you compute the left-right correlator, this should be zero if there was no interaction. But since we introduced the interaction term, it gets non-zero and it oscillates. And the frequency of oscillation should match the energy gap of the system. And also we noticed that running the simulation for parameters k of order 1, we would still also get close to the original SYK model, just like we were expecting. And there is also an indication that if you take larger Q, we can actually get close to the all-to-all SYK using a smaller value of K. However, if you compute the energy gap directly, we were expecting these two scalings here from the gravity perspective, but we only observed this scaling for Q equals H, so Q equals H body interaction for some large enough coupling. And for Q equals 4, we just don't observe that scaling that was predicted by holography. This
Sorry,
is quite
can
nice.
I interrupt you for a second?
Yes.
Yeah, I already did, but can you repeat what is K counting, please?
Yes. So K is counting the number of terms that we keep in the sum of the Hamiltonian. So the Hamiltonian is in such a way that has Kn terms in total.
Yeah, my question is just, because you just took on the right hand side of a slide K fractional, so that was I got a little bit confused. Does that mean that you keep half?
Yes.
Or something like that? Please.
Yeah. So the only condition for K is that K times Q should be an integer, a positive integer, larger than 1.
Oh, okay. That's why you said that.
Yeah.
But with bigger Q, you take smaller K and you keep this. Okay, thank you very much.
Yes. Okay, so what we have found is that what was nice, I think, is that we could find the scale that was expected from the gravitational analysis for Q equals H, which was only possible because of the sparsity property. So simulations for all-to-all SYK using like exact diagonalization, they only go up to 32 fermions. And if you try to do Q equals H, it's even harder because the number of terms goes like n to the Q power. So it was nice that we could see, even if it's just in a small range, this scaling that was predicted by holography. So this suggests that finite n effects, they are very strong in the Q equals 4 case, and also in this regime of small mu for Q equals H. So another thing that we were interested in is to, well, if you think about the traversable wormhole with the ADS2 geometry, if you send a signal through it was just go from one side to the other by obeying the causal structure of that space-time. And after it hits the other boundary, it's going to bounce back into the bulk, and it's going to start this oscillatory motion of going back and forth between the two boundaries. That's quite simple if you have the traversal wormhole in mind, but on the quantum many-body system perspective, what happens is that you create some perturbation on, let's say, the right system. Let's say you start with the ground stage, and then you create some Majorana excitation by acting on the ground stage. Then you let your system evolve for some time. What you expect that the excitation will get scrambled, and for practical purposes, the information of that perturbation just disappears. But due to the effect of the interaction, what happens is that this perturbation can get unscrambled and can reassemble on the other side, and you can recover information that you sent on the left system. And then the process repeats itself with the left and right exchanged. This is what we call revival dynamics. In this context in which we have an eternal wormhole, we call revival oscillations. So we want to find some diagnostic for this revival oscillatory behavior. And what we did was to compute the transmission amplitude, which is given by from the absolute value of some greater Green's function. And the square of the transmission amplitude is going to reflect the probability to recover the insertion at some time t after you inserted it at t equals 0. And based on this oscillatory picture of a particle traveling between the two boundaries, what we expect about these coefficients is that first, there are two independent coefficients, the t left and the t right left, or left right. And what you expect is that every time you see a peak in one of these coefficients, you should see a minimum in the other. That's what's consistent with this the picture that I just described before. And there's also an expected decay that comes just from the typical decay of the SYK correlation function. So we computed this quantity for the sparse model using the regular hypergraph, first at 0 temperature. So we are just looking at properties of the ground stage. And we didn't find the expected behavior of an oscillatory transmission amplitude with minimums and maximums of TLL and TLR. This didn't happen for Q equals 4, but we could observe it a little for Q equals H. This is somehow related to the fact that we could observe the scaling that was predicted by gravity for Q equals H, but not for Q equals 4. And if you go to higher temperature, then the behavior that perhaps it was not so easy to see in the previous picture, it becomes much clearer here. So you see a peak in T left right and have a minimum T left left. And the amplitude is going to decrease with time, just as you would expect from typical correlations of the SYK. So in summary, the Q equals H was like, we were able to see, to make a connection to the gravitational picture of the eternal traversable wormhole. We were not able to do this for Q equals 4. So this, the naive guess is that there is some suppression by 1 over Q, so that the finite N effects, they become less important for larger Q. And in summary, we have seen that the sparse SYK, it's useful because it allows us to explore this regime of intermediate values of N that for the ultra it was not possible to explore. And we could make this connection between the sparse SYK model and the eternal traversable wormhole of Maldacena and Qi, at least for some range of our parameters. So as a possible future direction, one natural one in this context of traversability is to find a relation with quantum teleportation protocols in which instead of having an interaction that's time independent, you just turn on the interaction at some time. And you should still be able to recover the signal, the quantum state that you want to teleport from one side to the other. There are also the out-of-time order correlators that have not been computed for this sparse SYK numerically. And essentially any other thing that was done for the original SYK model could be done for the sparse version, and we should be able to simulate it for larger values of N, do it to the sparse property. And just some comments about the numerical methods. I used this dynamite library, which is a Python library that works like an interface for two C libraries, PET-C and SLEP-C. They make use of Krylov subspace methods, and you can parallelize your code. That's how we're able to achieve the value of N that I showed. And we used the resources from the Texas Advanced Computing Center, TAC, to run our simulations. So I think that's what I have to say. Thank you. If you have questions, feel free to ask.
Thank you very much for the nice talk, Anderson. So let's see.